Hello everyone, today I'm going to show you how to read the Z table or the standard normal table. To refresh our memories, let's just draw the Z distribution, standard normal distribution, bell-shaped curve centered around 0. We note then that the area under the curve comes to 1 and also that it's symmetric. These two properties are important when it comes to looking up the probabilities. Now the questions we're faced with usually, we're given a point A, like here say, and we're asked to use the table to find like the area above A, or it could be below A, or we could be asked to calculate the probability that Z falls in an interval A to B, like so. Okay, there are three versions of the Z table, and that's why I tell my students at the start of the year, use the one, become familiar with the one that you're going to be using in the exam. Don't just use the one at the back of the book, because it might not be the one you're going to use. So here are the three versions. We've got the version that for a given point A gives you the area above or to the right of A, like so, first one. Another one gives you the area to the left of A, that's this one here. We call this the cumulative, standard normal. And there's one which I see less often, although I have seen it, is that it gives you the area between 0 to the point A, like so. Okay. Now, because I don't know which one you're going to be using in your course, for this exercise here, I'm going to solve it using each table. Okay, I'm going to start off with it in this video using the cumulative Z table, this one right here. But for all of these three, the procedure always is for a given problem to express that problem in terms of the inequality that your table uses. So for the cumulative, we have to express all our problems in terms of Z less than something. Okay, so even if you have a problem like, let's see, it's all less than, like 3 here, where you've got Z greater than 0.5, we've got to express it so it's less than some figure. Now you might be asking here, why isn't there just one version? Is the one version easier to use than all the other versions? The answer to that is no, because what you'll find is that for a given version, there's some problems which are easier to solve with that version than using other versions of the table, as you'll kind of recognize when we start to solve these. Look up these 6 probabilities using each of these tables. Okay, well that's enough background information. So we're going to start off with this one, which is the cumulative standard normal. And we're going to be using the tables, all three of these tables. We're going to use the one on my website, statisticsmentor.com. Now, because this is very important to what we're doing today, I just want to emphasize again that the area under the curve sums to 1, and also that it's symmetrical around 0. We're going to be using both these properties. Okay, the first one. Probably that Z is less than 0. So start off with a sketch. Once you get the hang of it, you don't need to do a sketch, but it's always a good idea to think about the picture. So that this horizontal axis is Z, all the way from minus infinity to plus infinity. We want less than 0, so let's shade it. Okay, well, by symmetry, we know that the area to the left of 0 must be equal to the area above. And since the area is 1, it must mean that half of the area is in this area and half is in this one. So the answer is, without using a table, a half. But let us just use the table to see that we do get a half. Okay, here is the cumulative standard normal table from statisticsmentor.com. We note that I've just got one friend at the moment on Facebook, but hopefully that will change. Okay, now the z here is on the border in bold, okay, and it's given to 2 decimal places. The first decimal place is given down this row, second decimal place is given down this column. Everything in the body is a probability to the left of the value I'm looking up. So we want 0 here, so we go to z to pick up the first decimal place first. It's 0.0, and second decimal place will also be 0 because the whole lot is 0. So where they intersect, along and down, we get a half. Okay, so that is the answer. Okay, and that's as much working as you need here, because it's directly from the table. Next, we're after the probability that z is less than minus 0.9. Now, the table only gives us values of z that are positive, so here we've got to rewrite this problem so we've got a positive instead of a negative. This is where the pictures come in handy. Now, by the idea of symmetry, you can see that the area shaded there must be the same as the area to the right of 0.9. These two are equivalent, aren't they? Yeah, it's like this one. I've just flipped over, and in doing that, I've changed the minus into a plus. Okay. So now we've sorted one problem. We've turned the minus into a plus. However, we've got another problem now, and that is that we've got z and we've got greater than instead of less than. Remember, I said that since we're using the cumulative table, we're just dealing with inequalities of z less than type. Okay, so we've got to now try to re-express this. Think about this picture in terms of how can I get it so that we're using z less than. Again, this is where you just have to think about a picture. Okay, and here it is. So I've split this into 2 bits. I'm saying that this shaded region is the same as the entire shaded region, and take away this area here. And doing that, you can see that it's the same as this area here, that z is bigger than 0.9. And this works because this here is probability, well, I don't even write in terms of probability, that's area under the curve, so it's 1, so let's write 1 immediately. And this one, the expression is that probability, you can see that it's z is less than 0.9, because that represents a shaded region, less than 0.9. And we can read off this from the table, because it is of the form probability z is less than some figure, 0.9. Okay, back to the cumulative table, we want 0.9, so let's pick up the first decimal place here. It's 0.9. For the second decimal place, we don't want anything, so it's 0. So we've got this column here, so we track it down to 0.9, where the intersect is this figure here, 0.8159. So that's what we want, 0.8159. Okay, substitute it in, and we've got the answer 0.1841. So that is what my solution looks like. When you become comfortable, you can kind of lose the pictures here. Right, so now we're after probability that z falls in an interval. Again, begin with a sketch. Okay, so we want that little strip there, the shaded region between 0.5 and 0.96. Right, we've got to kind of build this up so that it's in terms of the expression that z is less than a figure. Alright, here we've got probability z is less than 0.96, that's fine, but here we've got a greater figure. This says that z bigger than 0.5. So again, think of a picture where we can express the same problem but in terms of probability of z less than. Okay, so if you've had a think, I hope you've got this. This says that it's the area to the left of 0.96. Subtract that from the area to the left of 0.5, and that will end up with a little strip here. So writing that down in terms of inequalities with the z. So we've got two expressions now of less than, z less than something, z less than something. Both these we can look up. We want z less than 0.96 and also z less than 0.5. Z less than 0.96, as first decimal place, let's pick it up here, 0.9. So we want to run along here till we get 0.06. There. That's 0.8315. We also want probability that z is less than 0.5. So there you go. First decimal place 0.5. Second decimal place we don't want anything. So it's here 0.6915. And here you go. So the answer is 0.14. Okay. Now this is where Sketch helps. Sketch helps because first it can help us build up these inequalities. The other thing is that it gives us an idea of what value my probability should be. So this little strip here, we wouldn't expect an answer which is very, very big. So 0.14 sounds about right. If it was like, if we got an answer over 0.5, obviously then clearly something would be wrong. However, that statement that I made only works if your sketch is reasonable. So this is what you must be aware of, that by the time we hit the end tails, this value is around -2 and this value is approximately 2. Okay, I say approximately because basically it's almost hit the horizontal line here, but it's not 2, but it's quite close to 2. So that's why I've got 0.5 way over here closer to 0 rather than making 0.5 way out here. Okay, because I know that from here 0 to 2 looks like that. Well, explaining this to you guys, I can see it's actually taken longer than I thought it would, but that's good because I wouldn't really want to go through, it'd be too tedious to go through this in class. So any students of mine in class struggling should be watching this video. Okay, to the next type. Again, an interval, but this time what's from a spanner in the works. Look, I've got a negative here. Now, how do you treat the case where I've got an interval where I've got between a negative number and a positive number? Okay, here's a sketch. Think about how I can build it into 2 bits so that we've got the form that probability that z is less than. Okay, so see that it can be decomposed into 2 pieces again. Less than 0.67, which would give us a whole of this. But we want to get to also deduct this bit in blue. Okay, and that bit in blue is equal to this. That z is bigger than plus 0.67. So for z less than 0.67, we can get that directly from the table, cumulative standard table. This one though is to the right, so we know we cannot get that from the table, but looking at the previous examples we can see that this is simply 1 minus the area which to the left. So 1, that shaded region is 1 minus that probability z is less than 0.67. Here's where the picture kind of really helps. So if you're trying to figure this in your head, you might make an error. So look up the tables now. All we need is one figure, which is probability that z is less than 0.67. So 0.6 here. Then we'll run along till we hit 7. 0.67 there, 0.07. So we've got 0.7486. And here you go. Substituting the values now, we get the final answer of about around a half. Kind of makes sense. This interval here is around the widest point, so most of the area is contained in that widest point. Okay, 2 more to go. Right. Here we're after a probability that z is between an interval. This time we've got 2 negative numbers. Right, how do we deal with such a situation then, where we're looking for probability that z is in an interval between 2 negative numbers? Okay, so this is what the first picture looks like. We want to get rid of those negative signs, so flip it 180 degrees, we get this, so now they're both positive. Now we have to express that area so it's in terms of that probability that z is less than. Okay, so we've broken it down to difference of 2 chunks. Probability that z is less than 0.4, and subtract from that probability that z is less than 0.08, and we'll have our answer. Right, 0.4, the answer is 0.6554. And for 0.08, so one go up here, 0.0, slide along to a hit 8, 0.5319. And putting in the numbers, we get the final answer 0.1235. Okay, the final one, probability that z is less than 0.234. Right, what we've got here, we notice it's less than, so it's fine. It's a positive value, that's fine. But we've not got 2 decimal places, which is what the table reports up to. We've got 3 decimal places. So how do we get this figure? Okay, so what we know, let's just realize that when these tables were drawn up, we had very, very low computing power. So these days, proper statisticians would not bother with tables. So if we had 3 decimal, 4 decimal, whatever decimal places, the computer would give us the answer, okay? These tables only give us up to 2 decimal places, so what to do? Well, there's 2 schools of thought here. You could either just round up or round down the 3rd decimal place, or you can do interpolation. I'm not going to bother with interpolation here because I don't think it adds much value, but I know that some of you in your schools may learn about interpolation. Just want to focus, because it doesn't really affect the answer too much. I just want to tell you what I mean by rounding up and rounding down. Basically, we look at this 3rd decimal place. Now if it's less than 5, less than or equal to 5, we might round down, and anything bigger than 5 we round up. So in this case, if I use that rule, this would become 0.23. The question is, how do you treat the 5? Okay, so the first instance I said anything less than or equal to 5, I will just round down, and bigger than 5, I will round up. Okay. Or I could have just said, say it's got to be less than 5, then I'll round down. And if it's bigger than equal to 5, I round up. Alright? Either of these is fine so long as you're consistent. Now you could also say this. If it's less than 5, round down. If it's bigger than 5, round up. And if it's equal to 5, you take the average of the figure for the lower and the upper limit. So in other words, if this question was instead that z is less than 0.235, using this rule, I would say, right, sitting on the border, so what I will do is I will take the average of z less than 0.23 and the z less than equal to 0.24. Just take the average. So these two, that will be a value, that will be a value, add them together, divide by 2. Okay. That that would be interpolation at the value 5. But whatever method you use, whether you use interpolation, exact interpolation, which is a lot of slightly more work, doesn't really add much value, I just go for this. All right, but do check with what your instructor teaches you, and you should be fine. Okay, so if you're interested, I'm gonna produce another 2 videos repeating the same exercise but using the other 2 tables which are on our website, Statistics Mentor. I'm Phil. See you around.